We've defined the momentum of a system, and now let's look at the time rate of change of that momentum. So let's take the time derivative of this equation, d dt of both sides, and assume that the total mass of the system stays constant, so the system isn't gaining or losing any mass. So then the mass system comes out of our derivative, and we have d p sys dt equals the mass of the system times the derivative, the time derivative of the velocity of the center of mass, which of course represents the acceleration of the center of mass. And by Newton's second law for a system, the acceleration of the center of mass is equal to the net external force on the system divided by the total mass of the system. So we can replace this ddt of VCM right here with this ratio. So there it is. We have mass of the system times the net external force over mass of the system. That cancels, and we're left with the net external force on the system. And this basically represents Newton's second law for a system. And recall that this is combining the idea of Newton's third law as well. It's kind of built into this expression. So we've got the first derivative, the time derivative of the momentum of the system is equal to the net external force on the system, showing that only an external force can change the momentum of a system. Significantly, internal forces cannot affect the total momentum of the system. The instantaneous rate of change of the momentum of the system is equal to the instantaneous net external force. Oh, and since it's a vector equation, it really represents a separate equation for each component. So dp sys x component dt is equal to the x component of the net external force, and so on. All right, I want to rearrange this a bit more to get the impulse momentum theorem for a system. So we'll start by defining the net external impulse on the system over some time interval from time 1 to time 2. That would be this time integral of the net external force. And if we look at our N12 for a system up here, the net external force times dt equals dp sys, equals a small change in the momentum of the system. So this here says that if a net external force acts over a short time, that's going to affect a small change to the total momentum of the system. So this is dp sys right here. And so in going from here to here, replacing this with dp sys, we've changed our independent variable. It was time, now it's the momentum of the system, which means we need to change our limits of integration from t1 and t2 to the momentum of the system at time 1 to the momentum of the system at time 2. So again, our limits have to match the independent variable. And a change of independent variable requires a change in limits as well. Oh, and if we add up all these small changes in the momentum of the system, we get the large change in the momentum of the system, delta p sys. This is stating that a net external force acting over time, that is a net external impulse, that can change the momentum of a system. Let's summarize what we've come up with so far. We have defined impulse as this integral, the cumulative effect of a force acting over time. So the impulse over some time interval, t1 to t2, is given by this integral here. And I want to break down our equations that apply to a single object in this column on the left, and the equations that apply to a system in this column on the right. So we've got the definition for the momentum of one object, the definition for the momentum of a system. Then our version of Newton's second law written in terms of momentum. The instantaneous rate of change of the momentum of a single object is given by the net force on that object, and the instantaneous rate of change of the momentum of a system is given by the net external force on a system. So only a net force can change the momentum of an object, and only a net external force can change the total momentum of a system. Any derivative relationship can be rewritten as an average value relationship and as an integral. So this derivative can be, so if f is defined as this derivative, then the average value of f over some interval can be found by just replacing the d's with deltas. So dy dx becomes delta y over delta x, and our instantaneous value of f becomes our average value of f. And so replacing these derivatives with deltas over deltas, we get expressions for the average net force on some object is given by the delta P over delta T, and the average net external force on a system is given by delta P sys over delta T. Just replace these D's with deltas to get average value. And that's related to our integral that we can also write, which takes the form of our impulse momentum theorem. Here it is for a single object. The net force acting on an object over some time interval from time 1 to time 2 imparts an impulse, a net impulse to the object, which is equal to the change in momentum the object experiences. And for a system, the net external force acting on a system over some time interval from time 1 to time 2 imparts a net external impulse on the system, which is equal to the change in the momentum of the system. And we've got in front of us right here the ideas that represent conservation of momentum. Let's discuss those.